So here we are in the second video in the Getting Started series. This is where we left off is, yes, you can do procedural drawing because OpenGL can't tell where the Vertex 3F call came from. All right, other stuff. Color. So mentioned earlier on that there is a GL color 3F call. You pass in R, G, and B. Those are the principal components for computer display monitor graphics. The R, G, and B numbers are between 0 and 1. A lot of times you see them between 0 and 255. That's because that's how many voltage levels the colors actually can take. What OpenGL does is it says, let's go 0 to 1 in floating point, and the driver will change it into whatever integer the actual hardware needs. So this is much more device independent. This is known as additive color. You have reds here, you have greens, you have blues, and if you mix them, like if you mix some combination of red and green, so if up here, or red and blue, if up here you were to say 1, 0, 1, you would get a magenta. If you were to mix green and blue, so 0, 1, 1, you'd get cyan. And the really interesting one is if you mix red and green. Up here, if you said 1, 1, 0, you would get yellow. And this is just amazing to me because magenta does look reddish blue. Cyan does look bluish green. Yellow does not look reddish green, but it works that way. That's how your eye-brain combination works. And if you do equal amounts of all of them, red, green, and blue, you get, well, some white, some monochromatic. You could get black, you could get gray, you could get white. So this is how you pick colors in computer graphics. Transformations. You can move things around on the screen, which is good because that's how it happens in all your games, right? You can translate, meaning just pick something up and move it. Rotate, you can pick something up and spin it. And scaling, you can pick something up and stretch it. And there are OpenGL calls to help you do that. There's a call called translate, and you give it 3 numbers, and that's the amount to move in X, Y, and Z. There's a GL rotate F. You give it an axis. This is the axis of rotation. So if you wanted to rotate about the x-axis, you would do 1, 0, 0, but it doesn't have to align them with the principal axes. It can point diagonally up in the air. The angle is in degrees. This is the only place in, I think, all of computing where degrees are used instead of radians. It's degrees. Get used to it. And then scale. Now, scale is interesting. If you use the same 3 numbers, it lets you use 3 different scale factors. If you use the same 3, that's known as uniform scaling. And that's normally what we do. The object gets bigger, it gets smaller, but all its proportions stay the same. But there's nothing that says it has to work that way. So for instance, if I take a sphere and I scale it by 2 in x, okay, sphere, scale by 2 in x, but 1 in y and z, I have, well, a rugby ball, except it would really look like a rugby ball, not like that monstrosity I just drew. Scaling also has some other interesting things. What if I make one of the scale factors negative? That's perfectly legal. The math doesn't care. And what that does is give you mirror images. Okay, think of your left hand, hold up your left hand and your right hand. Those are mirror images of each other. That's what happens when you make a scale factor negative. You can also make a scale factor 0. What that does is flatten the object. It's kind of an interesting cheat to do shadows. If I want to make it look like I'm casting a shadow, I flatten the object, move it to the ground, and draw it in black. Okay, that makes it look like I'm casting a shadow. We'll look at better ways of doing shadows, but that's a nice cheap trick. So anyway, you can do all kinds of things with that scaling function. But What if you combine them? Okay. And here's the trick. First of all, the trick is you specify the transformations before you draw the object. One, specify transformations. Two, draw the object. Some people feel like you should draw the object and then come along and say, and rotate it. No, the rotate sets up some numbers that get applied next time you draw something. Okay, transformations come first. But what if you do more than one? So what if I do translate F, rotate F, scale F, like this? Well, the way it works is the one you specify last looks like it's going to take effect first. Okay, so it would look like you were scaling first, rotating second, and translating last. Okay, and we do this all the time. We compound transformations all the time because maybe you want to rotate something and then put it out in the scene where it belongs. Okay, you rotate here and you translate there. Whatever you do last in your code looks like it takes effect first. Now, why is that? Or how do you remember that? Whoops, think of this. Okay, here's my code again. Here's my GL begin, GL end. What if we just turn it all sideways? And here's the scale and the rotate and the translate, just like back here. Okay, if I was going to put parentheses around this, like I would do if it was an algebra equation, well, I would put parentheses here and here. That is the thing that's closest, the transformation that's closest to where you do the drawing. That would be inside the first round of parentheses. That's why it's done that way. That's how to properly think about it. And so really, it's like we've scaled these XYZs. Now we're going to rotate those XYZs. Now we're going to translate those XYZs. Okay, so as we go this way in the code, we're getting outward in the parentheses. Okay, just keep this in mind. That's how you can remember that the transformations closest to the geometry look like they take effect first. And of course, does it matter? Well, it does, because compound transformations are not commutative. Multiplication is scalar multiplication. 2 times 3 equals 3 times 2. The order does not matter. The order does matter in transformations. And I could prove this mathematically, but I'm going to prove it with an example. Supposing I start with this object. Okay, it's a square, but one of the vertices is red just so we can keep track of it. If I translate that and then rotate, so if I do this, I'm going to move it out here, and then I'm going to rotate. And rotates take place about the origin. So when I move it away from the origin and I rotate, really what I'm doing is I'm swinging it, okay, like that. Okay, so if I translate and rotate, it ends up right here. If I rotate then translate, well, if I rotate this, well, it's already at the origin, so now it looks like this, and then if I translate it, it looks like that. The fact that this and this are not the same result tells you that matrix transformations or transformations are not commutative. Okay, so the order matters, and you do that inside to outside thing. Okay, so OpenGL has a state. And think about the vertex 3F call. If I wanted to put in all the information about how to draw that vertex, well, I'd put in the XYZ, and I'd put in the RGB, what color to make it, and I'd put in 16 matrix elements, how to transform it, and then a bunch of stuff we haven't covered yet. Texture coordinates, normal vector, line width, all of that. I could make a 50 argument GL vertex 3F. Yuck, we would not want to do that. And so what OpenGL does is you set the state and then you do the drawing. And so when we said color 3F, that was an element of state. These things are called attributes. And what that means is you set them and they stay set for all the drawing that's to come. And they stay set that way until you change them. So if I want to do a red triangle then a green triangle, I would call color 3F red. I would call GL begin triangles. I'd give points. I'd call GL end. And then I would call color 3F again, green. And then GL begin triangle, XYZ, 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 GL end, like that. The color is part of the state. The transformations are part of the state. Again, you set them, they stay in effect until you change them. And there's a whole bunch of stuff in the state, and we'll see more of that later. All right, there's a stage in the graphics pipeline where we are going to do projection. Projection is how you change things from 3D to 2D. Okay, eventually we're going to change them into pixels on the screen. It's a flat screen, they're flat pixels. So somehow we've got to get the object flat too. There's two ways that that happens in computer graphics, something called orthographic and something called perspective. Orthographic, and you've probably seen these in art classes, orthographic lines that are parallel in 3D stay parallel in 2D. When you were a kid, you probably learned to draw a cube by drawing a square, drawing the exact same square, and then connecting up corresponding vertices. Okay, as long as the back square and the front square were the same size, that's an orthographic projection. Perspective is how we see things in the real world. Okay, objects that are farther away from us appear to get smaller. Okay, in orthographic they don't. This back square, even though it's farther away, is the same side as the front square. Okay, perspective is how we see the world. So if we see the world with perspective, why would we ever want to use orthographic? We do sometimes because it's useful for lining things up. If I want to draw something and then sort of confirm that this back face is the same size as the front face, that's much easier to do in orthographic than it is in perspective. Okay. Perspective also has this thing called a vanishing point, and again, you probably run across this in an art class. If you take lines on the object that go backwards, go back, and you just extend them, they'll meet at a certain point. And you can see this in artwork. Artists have used this for centuries, is pick a point and now make all the lines converge at that point. That's called the vanishing point. Yep. So here's a perspective drawing. There's the vanishing point. Here's the same thing in orthographic. The orthographic looks strange, but again, we usually use it just for comparing sizes. Yeah, there's nice cartoons about vanishing points and perspective. And so in your code, and you'll see this in the sample code, typically what we do is we have a variable that's a mode. Am I in orthographic mode or am I in perspective mode? And then we put an if statement here. So if I'm in orthographic mode, call this, else call this. You don't want to do both. Okay, if you do both, weird things are going to happen. But typically you bury this in an if else. And so now by changing that flag variable, you can change from orthographic to perspective. And we'll see this in the sample code. Yeah, and there's another way to think about it. If you're an orthographic and your eye is here, this is the part of 3D space you're seeing. It gets no bigger as it gets farther away, whereas in perspective, the amount of space you can see is bigger as you get farther away. Yeah, that makes sense. You stand on the rim of the Grand Canyon, you can see the Grand Canyon. Yep, because it's far away. In the GLU perspective call, there's an argument called FOV. It's the first argument. It's looking for a number of degrees. And that's the field of view angle. And what it is it's if my eye is here, that's supposed to be an eye, not a bug. Um, the field of view angle is how far up I can see and how far down I can see and what's the angle between them. Typically in computer graphics, you do 50 to 100. Big numbers like 150 is a really wide field of view, and it's like a fisheye lens. Really tiny numbers like 20 are like a zoom lens. You're only seeing a little bit of the scene, but it's blown up. But that's the first argument. The second argument is the aspect ratio, and it's the ratio of how wide you want to see divided by how high you want to see. Okay, if you want a square viewing volume, you make that aspect ratio 1.0, and oftentimes we do. If you were doing a cockpit, like in a plane, well, the cockpit windows are much wider than they are tall, and so maybe you would use an aspect of 3 times wider than it is tall. That's how you decide. And here's my favorite. My favorite OpenGL call is this one. There is a function called GLU lookat. It's got 9 arguments. The first 3 are where do you want the eye to be? The second 3 are at what point should the eye be looking? And the third is which direction is up? And this is how you can look at your scene from anywhere. Okay, if I want to look at it from the left, I can do that. If I want to look at it from the top, I can do that. If I want to look at it somewhere on a diagonal, I can do that. And you can hard code these numbers if you always want to look at it from the same place, or they can be variables. Your games, you're in a flight simulator. Well, you're flying through space. Well, all it's doing to make it look like you're flying through space is changing these numbers in the lookat call. Okay, so yep, this is great. I just love that. That's one of the things I've always loved a lot about 3D graphics is you can change your view. You can build a solar system and put your eye on Saturn. And wow, I can't do that in real life, but I can do that here. So yeah, GLU lookat's my favorite. This is a video I will show you. It's a fly-through of Chicago. They do a beautiful job of this. At times they change the eye position dynamically. At times they change the look-at position dynamically. It's just a beautiful thing. It was done years ago. That's why it's all lines, not polygons. If you know Chicago, this is north of the Loop, north of downtown. There's the water tower, if you know Chicago. But this is a video I'll show you just because of how they manipulate the eye and the look. They're essentially telling a fly-through story of Chicago. All right, supposing you've got a scene, you've got some object of a certain size, how do you set these things so that you can actually see the object? A lot of times we don't. We just throw it all up there and we scale the scene size up and down until the object fits. But if you want to do it a little more methodically than that. Okay, supposing here's my object, it's that big yellow star. I need to know the look at position, the eye position, look at position, and up vector. Well, okay, typically if we don't know anything else, we average all the vertices together to get the look at position. So right here is where we want the eye to look, right at the center of gravity of the object. I'm going to set the up vector to 0, 1, 0 because, well, we're always drawing with y going up. And I'm going to set the eye as level with the look. So I'm going to put the eye out here. It's got the same x, which we can't see, and it's got the same y as the look. This is z coming out this way, so we can't see x, it goes in. Now, if here's how, so the question is, how far away do I want to put the eye so I can see everything? Well, let's look at this triangle. This angle right here is 1/2 of the field of view angle used in GLU perspective. If I take half of h divided by how far away the eye is, that's going to be the tangent of half of the field of view angle. Math, 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 and we find out we need to move the eye that far away, and we need to set the field of view angle to this. Okay, so you can do it mathematically, but a lot of times we don't care. We just throw the object up there and then scale it up and down until we can see everything we wanted to see. Also, there is a function called GL viewport that you'll see in the sample code. And this is a way of restricting the drawing of an object to some sub portion of the window. So here is the whole window. Yep, you can see the little window title bar and all that, but I want to draw my graphic scene here. Okay, what do? I call viewport. It's got 4 arguments. The first 2 arguments are, where is this point? Now, most of us think of 0, 0 as being lower left. The viewport call, for some reason, makes 0, 0 the upper left. So we're doing x left, and we're doing, well, y comes down from the top. Again, you just get used to it. dx and dy are the width and height of the viewport. Okay, so the code you've got is set up to try and make the viewport fit the whole window, but you don't have to. You know, you could have multiple viewports of different views of your object. That's real common for us to do. The only trick is you've got to make sure that the aspect ratio matches. The x divided by y here has got to be the same as this x divided by y aspect ratio there. Otherwise, you're going to get distortion. If you're doing a cockpit window, your aspect ratio in the perspective call may be 3 to 1 wider than tall, but then your viewport had better be 3 times wider than tall. Okay, so yes, otherwise you get distortion, and yep, you'll know it. You'll recognize it that your scene is now scaled in a funny way. And one more thing, and you'll probably need this in project 2. You can save and restore the transformation. And the calls to do this are GL push matrix and GL pop matrix. They are very unfortunate calls because they expose the fact that transformations are stored in matrices. Normally, we wouldn't need to know that. We call it translate, we call it rotate, we call it scale. But here they decided it was smart to expose the implementation. No, you don't expose the implementation. But there's a matrix stack. And so you remember from CS261 how stacks work. It's last in, first out. That's how it works. And so if I want to do this rotate and scale, but then when I'm done doing my drawing, I want to get rid of the rotate and scale, well, I do a push matrix here and I do a pop matrix there. When I pop the matrix, it's what the matrix was, what the overall transformation was right here before I did the rotate and scale. And so that's why we use it. And again, this is going to show up in project 2. So there we have it. There we have a whole bunch of the nuances of doing OpenGL programming and what some of my favorite functions do. And next we're going to look at the sample code. So come on back for video number 3.